So don't overthink this. Everything that worked in 2 dimensions also works in 3 dimensions. So let's go. We've got vector A plus B. Now A is 2i plus 2j minus k. And then I'm going to add, and I'm going to put the next one in brackets, because sometimes if you're dealing with negatives, things can get funky. So we're going to do negative I plus 2j plus k. All right, so let's take a look at what we've got. We're just grouping like terms now. 2i plus negative I. That's going to leave me with just I. 2j plus positive 2j. So that's positive 4j. And then negative k plus k. That gives me 0k, right? And so we don't have to put it there at all. They cancel each other out. I plus 4j. So interestingly, we started with 2 3-dimensional vectors, but the k components end up cancelling each other out, and we're left with a nice 2-dimensional vector, I plus 4j. Next question. All right, so I'll work this one down here. Now, c is simply 4k, right? So we could think of it as like 0i plus 0j plus 4k, but we can just write it as 4k. Now, minus, and then we've got to be careful here, right? Because we're subtracting all of this next bit. So we're subtracting 4 times, and then what are we multiplying? We're doing a. So 2i plus 2j minus k. All right, best to expand this bracket first. So we get 4k minus 8i. So it's negative 4 times 2i, which is negative 8i. And negative 4 times positive 2j, which is negative 8. And then negative 4 times negative k, which is positive 4k. All right, let's group these like terms. But when you do this, put the i's first, right? It would be so weird to do it any other way. Negative 8i, negative 8j, alphabetical order, and 4k plus 4k is positive 8k. I's, j's, and k's. It's like a coordinate system, so you would always put them in order. Okay, finally, last question. We're looking for the magnitude of b. Now, it works exactly the same as it does in 2 dimensions. We are doing the square root of all of these bits. So it's negative 1 squared plus positive 2 squared plus 1 squared. All right, that's the same as 1 plus 4 plus 1, which is 6. The answer is root 6. Bit strange to have this big long thing, but hey, whatever. All right, there are 3 questions done. Next one. So for these 2 questions, very like knee-jerk reactions. We've got points A, B, C, D in 3-dimensional space, right? And we're trying to find vector AB. All right, so no thinking, automatic. AB is equal to the second value, OB, minus the first value, OA. Okay. Now, OB can also be expressed as just the position vector, right? Here. So we've got OB, which is 5i plus j minus 6k. 5i plus j minus 6k. And then we're subtracting, careful, because you've got to subtract the whole lot. We're subtracting a. We're subtracting I plus 3j minus 2k. Okay, we've got 5i minus I, which is 4i. We have j minus positive 3j, so minus 3j, which is negative 2j. And we have negative 6k minus negative 2k. So we have negative 6k plus 2k, which is negative 4k. That's it. That's vector AB. That's the vector connecting point A to point B. So I am scared that I might be wrong. So the way that I double check is I say, okay, this is point A, right? 1, 3, negative 2. And this is point B, 5, 1, negative 6. So then I can sort of double check my work by saying, okay, how do I get from 1i to 5i? Well, I add 4i. That's how I get from A to B. All right, how do I get from 3j to j? Well, I subtract 2j. All right, that makes sense. And how do I get from negative 2k to negative 6k? Well, I'd subtract 4k. All right, good. I've double checked my answer. I know it's correct. Okay, next one, CD. Again, very knee-jerk reaction here. OD minus OC. All right, I've got OD, which is 2i plus 4j plus k. And I am subtracting, careful, OC. I'm subtracting 5j plus 3k. Notice there's no I component here. That's fine, it's like 0i. 2i minus, there's no I, so just 2i. 4j minus 5j, that's negative j. And k minus 3k is negative 2k. Just like in the last question, I can double check. If I want to get from point C to point D, all right, so no I, so 0i, 2i, I'd need to add 2i. If I want to get from 5j to 4j, I'd need to subtract j, yes. And if I want to get from 3k to k, I would subtract 2k. Okay, done. I know I'm correct. Next question. So for vector OD, because we're calculating from the origin, this kind of deal doesn't work, right? Because we end up in this weird situation where we say it's equal to OD minus OO, which doesn't make sense. So instead, we're just looking at the point D and trying to calculate vector OD. If we know the point D, then we know vector OD. And so the point D, you can see it's in line with point A. It's directly like above it. So that means it's the same outwards, right? Now we haven't moved anywhere in the Y direction, so 0, and then it is up, and it's in line with G in terms of its height, so that's 3. 5, 0, C, 3. So vector OD is equal to, and we can express this, if we like, as 5, 0, 3. We can also express it as 5i plus 0j, we wouldn't put the 0j in there, we'd put plus 3k. You know, I really should remember to put my squiggles on everything. All right, that's OD. All right, what about DC? You know, knee-jerk reaction here, DC is equal to OC minus OD. This is something that's automatic. Now, I haven't even looked at my picture yet. Where is DC? All right, so D is here, and C is here. All right, so we're going from the top corner here to the bottom corner here. Not that it matters too much, because if we can do this, we're fine. Now, we were given OC in the question. We know that it's 2J. And then we're subtracting OD from it, which we just calculated. Again, be careful when you're subtracting vectors. 5i plus 3k. All right, and then we have negative 5i, putting my I value first, positive 2j, and minus 3k. Squiggles everywhere. My answer is negative 5i plus 2j minus 3k. Now, like, think about it. Does that make sense? Well, imagine getting from here to here. You can pass straight through the center of the rectangular prism, or if you were like an ant, right, you might travel from here down, which is the negative 3k bit, and then you might travel from here to here, which is the negative 5i part, and then you might travel from here to here, which is the positive 2j part. So it makes perfect sense. All right, last question. So we're trying to find the magnitude of vector OE. Be careful, there's these lines here that mean we're trying to find the magnitude. Now, I don't know what vector OE is, and this knee-jerk reaction doesn't work because we're going from the origin to E. So we really just need to know what the point E is. All right, so E is like 5 out of the page. It is 2 across the page, and it is 3 up the page. It is 0.523. It takes all of this stuff into account. So we're going to find the magnitude of vector 5, 2, 3. You know, you can swap between I's and J's just depending on how you're feeling and what's easier to do at the time. All right, the magnitude of that is equal to 5 squared plus 2 squared plus 3 squared, and then find an answer. All right, make myself a bit of space here. It doesn't look like we're going to get anything neater than root 38. It's about 6 point something. And again, you can double check to make sure that makes sense. If this length is 5 and this length is 2 and this length is 3, to get from there to wherever we are there, right, it's going to take a bit more than 5. So an answer of like 6.1, 6.2 or something, that feels good. Okay, next question. So funny thing happened, the power went out, so I had to stop filming. I went and got a haircut, I put my contacts in, and we're back. All right, so let's do this question. We're looking at dot products here, and super simple, works exactly the same as it does in 2 dimensions. So I've written out the first question in full, and then we're just doing 1 times 2 plus negative 4 times 3 plus 7 times 3. All right, and then like whatever that is. All right, easy done, 11. All right, this next question here, not too difficult. We're just going to add those things before we do the dot product. So we can work flexibly here. I've got everything in I's and J's and K's, but I can write it all in column notation if I want to. So we're going to do A, which is 1, negative 4, 7, and we're doing the dot product of, and then I'll put these in column notation as well, B, 2, 3, 3, plus C, which is negative 1, negative 2, 1, negative 1, negative 2, 1. All right, and so then we don't worry about the dot product, so we'll leave that for a second, and we'll do this addition, which is going to give us a single matrix. You can do that. And then having it in column notation like this makes dot products pretty simple because it's 1 times 1 plus negative 4 times 1 plus 7 times 4. And then just calculate that. And we get a final answer of 25. We can work in J's and K's, we can work in column notation. It's all good. Next question. All right, so a fun little dot product question here. We've got a vector, we've got another vector, the dot product of which is equal to negative 6. The thing we don't know is this x value here. All right, so we just do the dot product, right? So it's 1 times 5, and then 2 times x, which is just 2x, and then it's negative 3 times 1. And all of that is going to be equal to negative 6. All right, simplifying that a little bit, we get 5 plus 2x minus 3 equals negative 6. 5 minus 3 is 2. Move that to the other side as negative 2, so negative 8. And then x is equal to negative 4. All right, done. Of course, you could always check that. You could put negative 4 back in here, and then do the full dot product again, and you should get an answer of negative 6. All right, so if A and B are the points defined by these vectors, use the dot product to determine the angle between these two vectors. So this is really where the dot product is super useful, finding the angle between two vectors in 3 dimensions. It's impossible or very difficult to draw and picture it, but very, very easy if we just use our 2 formulas for the dot product. All right, so I've written it up. I've chosen to convert them to column vectors just because. This I'm going to find the dot product of, and that's going to be relatively straightforward. I need to find the magnitude of A and the magnitude of B. So let's just do a little bit of working maybe over here. The magnitude of A, square root, and it's 1 squared, 2 squared, and negative 1 squared. That's going to give me a magnitude of root 6. And then let's find the magnitude of B, which is negative 1 squared, and negative 3 squared. All right, that gives me 1, 1, and 9, which is root 11. Now I can put those into here. So I get root 6 times root 11 cos theta. And then on the left-hand side, I can do that dot product. 1 times negative 1, let's do it fast, is negative 1, plus 2 times 1, which is 2, plus negative 1 times negative 3, which is 3. Okay, negative 1 plus 2 plus 3, that's 4. I can divide that by root 6 and root 11, and I'll be left with cos theta. And of course, theta is going to be equal to the inverse cos of 4 over root 6 root 11. Calculator time, and we're done. And we get an answer of 60.5 degrees. Done just like in 2 dimensions, only in 2 dimensions you could kind of come up with a way to do it that didn't involve this. In 3 dimensions, if you're not using the dot product, man, your life is going to be so much harder. That's it.